In the previous lecture, we were talking about recursion. We saw about recursive design and recursive thinking, and we solved a few problems recursively using this idea of functions calling themselves to create the engine of repetition. So we're going to take this idea of recursion and now apply it to the searching and sorting domain, starting with our old friend, binary search. So binary search is a searching problem, so it starts with the inputs of a list to search and a key that we're looking for. With binary search, though, we also make the assumption that the input list is in sorted order. Then the idea is we start by searching somewhere near the middle. We look at the middle item and say, is this the one we're looking for? If so, great, then we're done. If not, we have to then look through one of the remaining halves of the list, depending on how the item we are looking at matches up to the key. If it's greater than, then we look to the left half. If it's less than, then we look to the right. Now, we're going to solve this using recursion today, but the recursive version of this isn't any better than the iterative version. It's still going to solve the same problem. It's going to solve it roughly as fast as well. And in fact, the recursive version might even be a little bit slower because of that overhead we mentioned before. Each time we make a function call, it takes a bit of memory, a bit of processing power to do all the bookkeeping that's necessary. Yeah, so let's just jump right into it. Let's create some code. So a new file here, binary search.py. So the function binary search takes in a list and a key and attempts to find that key in that list. So let's just do the version where we're returning true or false here. So with all recursive functions, we need three things. We need a base case, the end of our search. We need a recursive case that puts some repetition into our code. And then we need something in that recursive case that shrinks the problem to make it a smaller problem. It moves it towards our base case. So to find a base case, think about what's a version of this problem? What's something the user could call this function with, some inputs the user could call this function with, where we don't really have to solve anything or do any work in order to come up with the answer. For a searching problem, that's pretty easy. If we have a list that's so small it has no items at all, then the key definitely isn't going to be in there. So we can say, if the len of our list is equal to 0, then return false. So there's our base case. Put that there, base case. Otherwise, there's some list in there. We should probably search through it. Now, the idea behind binary search, again, is we start with the middle element. And if that's the one we're looking for, great. If it's not, then we figure out where the remaining of the search needs to go. So we need to start with some sort of middle value. Now, when we're shrinking our list, the list is going to get smaller and smaller and smaller and eventually be 0, which is to say we're actually shrinking the size of L when we're going to be taking halves of the list each time. So the middle point is always just going to be the middle point of the list itself. We're not moving indices around like we did in the loop version. In this case, we're actually just shrinking the list. So we can say the len of L divided by 2. Floor division, so we avoid some of those decimal points. So we have the middle of this list. Next, we want to know, is this the item we're looking for? So if L at mid is equal to key, great, we found it. Return true. Now notice this is another base case. So there's nothing wrong with having multiple base cases. In this case, we have a failure base case and a success base case, one where we didn't find the item and one where we did. Both of those will stop the search. There's two situations where we should stop the search, so it makes sense to have two branches of our code for those base cases. Now, if it's not one of the base cases, then we need to worry about the recursive case. So if the item we're looking at isn't the key, we need to know, is it bigger than or smaller than the key? So we can say L if L at mid is less than the key. So the item we're looking at is smaller than the item we're looking for, and the item we're looking for must be to the right of this, right? It must be in the back half of our list. If we have a list 1, 3, 5, 7, 9, 11, let's say, and we took this as the item we're looking at, say the 5 here, and we're looking for, let's say, the 9, then it has to be in this half. So if the item we're looking at is smaller than key, we go to the right. And for this problem, what we'll actually do is we'll take a given list and we'll just shrink it down. We'll just say, okay, well then I'm only interested in the remaining items. So we'll call binary search on a slice of L. So L from 2. Now, the starting point of that slice is going to be the place that we just looked, the midpoint. So mid, and we don't care about that mid element being in this result either, so we can actually just say mid plus 1. And the ending point of this slice is right up to the end of the list. It's everything from the mid to the end. Okay, and we're still looking for the same key, so key there. Now, this binary search, this call here, is going to return true or false. It's going to return true if it finds the key in the back half of the list, and false if it doesn't. Which means if the user calls binary search on the entire list, and we're delegating that search to another call, then whatever this other call returns, we should return as well. So we're going to return whether or not we could find the key in the back half of the list. If yes, then we'll return true. If no, then we'll return false. Okay. Now, the item's not in the middle. It's L is not less than the key, so our else case is that it must be greater than the key, which is to say the key is a smaller value. So we will do a similar thing. We'll do a binary search down the front half of our list. So we'll take the opposite slice from the middle up to, but not including mid. So let's test this code out. Python-i binary search.py. So let's create a list. L equals, it needs to be in sorted order. So we'll say 1, 3, 5, 7, 9. There we go. Just a bunch of odd numbers. And let's see if we can find something in there. So we'll do a binary search on L for, let's say, the value 3. True. And let's do a similar search for, let's say, the value 10. Now, no even numbers in there, so 10 shouldn't be in there. And we get false. So it's doing the exact same work as the other binary search, just now it's doing it with a recursive pattern. Now, as I mentioned before, this binary search is limited. It's going to have a bit of overhead, and there's also the issue of Python's stack limit. Remember when we were doing recursion, we saw if we don't control our recursion properly, we could get unlimited recursion or an infinite recursive loop. Now, in Python, there's an upper bound on the amount of stack frames that you can put on the call stack that's set to 1,000. We can see that here, def hello. Create a function called hello, and then call that function. There we go. So the maximum recursion depth exceeded, which means this binary search is limited in the size of list that we can search, because each time it makes a comparison, it's then going to call a version of the function. It's going to add another stack onto that frame. Now, if we were solving this problem using a recursive linear search, then the size of the list that we could search meaningfully would be 1,000, right? Because each call to linear search would check one item. If it's not it, we'd throw it away and shrink the list to the remaining 999 items. So in the worst case, we'd have to go through all those items. So it would be 1,000 would be the maximum number of items. With binary search, though, when we make one comparison, we throw away half the list. So then we call binary search on a list that's half the size. And then we do that again and again and again. So the number of calls we can make is still 1,000, but the size of the list, the original input list that would make it so we'd ever reach 1,000 calls is actually 2 to the 1,000, which, as you can see, is a particularly large number. So we don't have to worry too much about that limit for Python. It's very likely you're not going to have a list with, I don't even know what the words for that number would be, but with that many elements in it. So yeah, don't worry too much about that limit here, but do be aware that there is some extra limitations when we apply recursion to our problems. Okay. Now, with this problem, we're returning true or false, but we've seen binary search. It can also work on returning indexes. So let's also attempt to solve that. Binary search index. So it takes in the same information. It's still going to do the same process. It's going to determine, is the item there? But now it's also going to tell us, if so, where was it? Now, there's a bit of an issue if we use this version. If we just returned this, if we had false, that would become -1. That's easy. But if it's true, if we return mid, then we don't want to just return that value, because the mid for a smaller list isn't the mid of the entire list anymore. So it's going to return the wrong value. So if you have a list like 1, 3, 5, 7, 9, let's say we're looking for the 7. We shrink the list, we see 5, and then we have this new list. That's just 7 and 9. Now the indexes of these things are 0 and 1, but the indexes originally were 0, 1, 2, 3, and 4. So we don't want to just return that value. There's some work you can do. You can try and figure out how many items you're removing and then add that to the result. But that's a lot of extra work. So instead of having just the list and the key, we will have a list, a key, and like we did with our iterative version of this problem using loops, we'll keep track of the start and the end of the loop as well. Now, to do that, what we're going to actually do is create a helper. We don't want the user of our function to have to know this extra information. We don't have to every time we call binary search, also pass in 0 and the length of the list. So we'll create a helper function here. We'll say binary search helper. So we'll call another function. And we'll pass in the list and the key. The list and the key. And then the starting and the ending indexes. So 0 and the length of L minus 1. Okay. So binary search index here, this function, is not going to be recursive. It's going to call binary search helper, which will be recursive. And that's going to give us back some information. We'll just return whatever that is. So you can think of this as the public version or a wrapper around, this as a public version or a wrapper around the actual work that binary search helper is going to do. So def binary search helper takes in a list, a key, a start, and an end index. Okay. Now the function that we're calling as the end user here, it's not recursive itself. It's known as indirectly recursive because this binary search helper function is going to do work similar to our previous version where the function was calling itself. Sorry, I should fix this. This is false. This is true. Okay. So we still need a similar setup. We need a base case and a recursive case and something in that recursive case that moves us towards the base case. But what we're going to be using to shrink our problem now is the distance between start and end. Think back to how we did this with regular binary search. Start starts at the beginning, end starts at the end, and every time we do a comparison, rather than taking a slice of our list, we change the indices. So either start move to mid +1 or end move to mid -1. So same sort of thing, which means our base case is going to be a little bit different now because our list is never going to change. It's not going to suddenly have no elements. The thing that will change are these. So our base case now asks if start is greater than end. Start should be less than or equal to end. As soon as start passes end, then we've run out of things between them. At that point, we can return -1. We don't have the value. Okay, then we can call the rest of our work. So we get mid, which now, again, we have to figure out the calculation for mid works the same as it did before. So start plus end divided by 2. And then we do the actual searching part. So if the item at mid, so if L at mid is equal to our key, great, we found it. But now notice mid here is the actual location of that item in the original list because the list itself is not going to change. So if we found the item at index mid, then that's where it is. It's not going to be, we don't have to do any calculations to figure out how we shrunk and sliced this list apart so that when we're going back to the original list, we have to make some sort of mapping. In this case, mid is where it is, so we return mid. Okay. Now, if it's not that case, elif, then the item is either less than or greater than our key. So if we'll say if it's less than our key, so we're looking at a 5, but we're looking for a 9, then we need to look into the right half or the back half of our list. So we'll do a binary search helper with new values. So L and key don't change, they're the same always, and we get new values for start and end. In this case, the value we're looking at is too small, so we need to go to the larger size of this list. So we'll say mid +1 as our new start, and end stays where it was. So we'll move the mid, or move our start point up to the current midpoint, dropping off the front half of the list. Okay. Now binary search is eventually going to return a value, so we can just return whatever binary search gives us. That will either be mid or -1, our two base cases. Finally, our else case just says return a similar thing, but the other side. So the item we're looking at is too big, so let's look at the small side of this list. Again, the list and the key don't change. In this case, we don't want to change the start because we still want to look from the beginning of the list up until mid, and we want to stop at mid -1. Okay, so let's test this out. Do I still have all my commands from before? I do. All right, so let's create the same list, and we use binary search _index on that list. And we'll go looking for, let's say, the value 3. And it finds it at index 1. That's great. We could try another one. How about 11? Finds that at index 5. 0, 1, 2, 3, 4, 5. Seems to work. And binary search for something that doesn't exist. Binary search index L for a 4. We get -1, signifying that it's not found.